Well, so I will start with two good news, because we have to stay positive. And the first one is, yes, I'm going to talk about coherent states. So if you're a fan of coherent states, well, I will introduce them for the probably third or fourth time today. But well, the second good news is if you are bored to death by coherent states, I believe this is the last talk today about them. So let's start. Well, so when I usually tell physicists that I work with coherent states, the common misconception is that, oh yeah, okay, coherent states, yeah, I know. Well, but what's interesting in there? Well, so the thing is that most of the physicists think that the story of coherent states ends exactly when the Erwin Schrödinger introduced them in 1926, and well, they were seen as just an eigenstate of the annihilation operator, and well, one can solve the differential equation and just obtain those states. Well, they have two parameters. Well, I will conveniently call them Q and P. And well, one can look at different properties of this family of states. And well, except being the eigenstates of the annihilation operator, well, one can see that they are created by the action of Weyl-Heisenberg group. Well, so just with action of dilation operator on a Fock vacuum. Okay. Well, the third property is that they saturate the Heisenberg inequality. Well, that's also some observation. And well, they are over complete, right? So they have this kind of resolution of identity. And well, so basically, if you want to somehow plot them on this parameter space Q and P, there will be just like Gaussians, and they are moved from the point 0, 0 by displacement operator to some point. There will be a Gaussian in here, and when they evolve, they just rotate around the point 0, 0. Well, and in fact, well, if we interpret, I will talk about it a little bit later, this Q and P as a position and momentum, well, or just calculate the expectation value of the position of the momentum and position operator in those states. In this, sometimes they are marked with alpha instead of QP. Don't worry about that. We'll see that they have this classical motion of the harmonic oscillator. And well, this is a first hint that in fact those states somehow relate the quantum mechanics and the classical mechanics. They behave very classically. And well, the thing is, well, the physicists like to generalize some ideas, right? And maybe they will see something more in those simple ideas. And the idea was to somehow also generalize this standard Schrödinger coherent state. And well, so the thing is to look at those properties and somehow choose those that will allow us to find some wider class of coherent states, but so not to narrow them down too much. And basically, we cannot use this property because, well, this completely fixes the form of the coherent state to Schrödinger coherent state. Well, saturation of this inequality, well, I believe it will just give us, if we stick to this, it will just give us always the Gaussians. So it's also not very interesting. But well, we can stay with just those two postulates. So the coherent states are created by some representation of the symmetry group on some state, and that they were all over complete. And well, that's how I will introduce the generalized coherent states. And well, so exactly, the first point is they form an overcomplete family of states. So we have some classical labels. We still don't have to somehow recognize them as some physical observables yet. Okay, and we have some continuous map from this set of labels, parameters, to some states on a Hilbert space, right? And they are we want them to be over complete, so they have this kind of resolution of identity. There may be some constant in here, right? We talked about today about this Schur lemma. Okay, so the second thing that I will somehow postpone yet is that, if we have this kind of abstract definition, we can connect those labels to some physical observables. I will postpone that, and I can just tell you that usually they will be just the position and the momentum of the state. And the second thing, the connection between the states and the symmetry groups. And in this case, we want to have some unitary irreducible representation of some symmetry group on a phase space. So now we will assume that those labels mean something, and we want to create the coherent states by just action of this operator on some state. And so couple of things are important. Let's focus on this fiducial vector. Exactly, this is called a fiducial vector, and we'll see that it will be extremely important soon. One can see easily that in fact the Schrödinger coherent state is in this family of generalized coherent states. It has this overcomplete resolution of identity. The two labels are Q and P, and in this case the operator is just a displacement operator, right? So two more slides of the introduction, and we'll get to something new. But during this presentation I will focus on two symmetry groups that will be important. I would like to focus on Weyl-Heisenberg coherent states. So this is a 3-parameter group with every one of the parameter is defined on a real line. And the algebra, the action of the group element is the following. So those thetas, they mix non-trivially. But Q and P, they are just summed up together. And if we think about it as Q and P as a position and momentum, we can see that those are just a translation in position and momentum. We have also the irreducible, unitary irreducible representation. There's infinitely many of those, but I choose the most convenient one in this case. And so with action of this representation on a fiducial vector, we get the coherent state, the Weyl-Heisenberg coherent state. And we can see that it looks like this in the position representation. The theta serves as a constant phase, and most of the people, and I'm one of them, just don't care about theta. That's the overall phase in front of the state is not physical, as Andrzej Guść told us before. So we can also see that just acting when we omit theta, we can act with the displacement operator on some state on this fiducial vector, and that's how we obtain the the Weyl-Heisenberg coherent state. And the second group, the second type of coherent states I would like to, well, present, where they are affine coherent states. So right now we have two parameters. The P is defined on real line, and the Q is positive. So basically, it means that, well, in this case, we cannot add them these Q's, right? Because if we want to have inverse element, we'll have to subtract them, so there will be a risk that will somehow get outside of R plus, right? So the correct action is just multiplication in Q's, and well, P's are on real line, so actually we can just add them up. We divide by Q, well, because we want to have this connection to the canonical transformations, but that's not extremely important. We have a unitary irreducible representation. There are three of them. As usual, I choose the most convenient one. And maybe one more thing. With this kind of action in here and this kind of action in here, well, we can identify the neutral elements and inverse elements, which will be important a little bit later. Obviously, the neutral element in Weyl-Heisenberg algebra is 0, 0, 0. The inverse is just minus everything. In the case of affine algebra, as we have the multiplication here, the neutral element is just 1 and 0 in momentum, and then, well, we have the neutral elements in here. Okay, so the last slide of the introduction. Yeah, and well, so as I said, well, quantum gravity, if it even exists, right, seems to be hard, extremely hard, right? So maybe we can take some semi-classical approach to it, and well, that's what I will try to convince you that it's worth it. And well, how do we do so? Well, so we can start with the action for, well, quantum mechanics. This kind of action, well, generates the Schrödinger equation, and the standard way to introduce some semi-classical analysis is to just restrict our Hilbert space to some, well, Hilbert subspace. And well, that's what we do.
It's not a subset.
Subset, yeah. Yeah, sorry, exactly. Well, so we do so, and we choose the states we use as a coherent states. And why? Well, because after we calculate, let's say, this effective action, well, we have this very convenient and nice form of our action. It looks like just a Lagrangian, right, or just a Legendre transformation of Hamiltonian. Well, we have Q and P, not yet, they are still just some parameters, and some Hamiltonian, right? Well, so from this action, by variation with respect to Q and P, we can have Hamilton-like equations for those labels Q and P. And well, why Hamilton-like? Well, because this is not a classical Hamiltonian. This is a expectation value of the Hamilton operator, Hamiltonian operator in the coherent states, and it can, and usually does, have some quantum corrections inside already. Okay, but those Q and P right now are still just some parameters. We don't know what they are. They're still very abstract. To actually fix the physical meaning of those, what people usually do, and I will do this also, we just set that the expectation value in the coherent states we use of the position operator is exactly Q, and the expectation value of the momentum operator in those states is exactly P. And these conditions translates exactly that the expectation value of those operators in just a fiducial vector, right? Well, corresponds to the neutral element. So for Weyl-Heisenberg algebra, we get, well, 0 and 0. For affine states or affine group, we have 1 and 0. Okay? And, well, this procedure of, well, giving the interpretation for those labels is usually called the physical centering. And, well, usually it's a little bit like skipped. People don't think about it too much. But, well, so I do, and you'll see why exactly. Well, so the picture is the following. Now, well, we have some Q and P, which are which we understand as average position and average momentum. So we have some, let's call it phase space in here. There are some points on this phase space, and for example, if we have some neutral element in here, neutral element, so 0, 0 or 1, 0 in here, well, it corresponds to some fiducial that we chose. Okay, so this line corresponds to different fiducials that give us the neutral element when we take the expectation value of them in the coherent states. And what one usually does, just acts with the group action, right? So the whole the state moves from one point on this phase space to another, right? But, well, so I believe that the new idea that I would like to introduce is that, well, so the this condition of physical centering can be satisfied by infinitely many fiducial vectors. Those are just, well, very trivial conditions. And, for example, well, symmetric wave function just satisfies, every symmetric function just satisfies this condition. So what we can do is, in fact, parameterize different fiducial vectors with some additional parameters, let's call them lambda, in such a way that with change of lambda, we still, well, we just, let's say, choose a different fiducial vector that gives us the same physical centering conditions. And during the evolution, when we drive our evolution by the, well, variation of action with respect to Q, P, and those additional parameters, the state on which we spend our, well, the coherent states will also change a little bit, and it will change accordingly to, well, how it should behave in quantum mechanics. The state will, for example, squeeze a little bit or disperse a little bit, and, well, it will be well suited for the motion we have. And, well, I think that we can get some more information, well, from this kind of analysis. And, well, yeah. So the thing is that, so if we allow the fiducial vector to depend on some additional parameters, well, we can again calculate this semi-classical or this action, reduced action. In this case, I use subscript E because there's something new in here, right? We get some additional term in the action, and in fact, it will drive this kind of motion in those additional variables that we put in there. Well, so we also get the, well, we get the semi-classical Hamiltonian. It will also in general depend on those additional variables. And, well, so if we had the standard picture, we just assumed, well, we started from the state that satisfied these physical centering conditions. In this case, well, there's a possibility that this state, well, will somehow get outside of those conditions. They'll leave those conditions. So we have to input them, well, explicitly as a constraints with some Lagrange multipliers, C2 and C3, because there's also C1 for normalization. I will mention it soon. And those constraints are of the second kind, And now we obtain the improved Hamilton-like equations. So the same for Q dot, the same for P dot, and additional equations for the additional variables. And what I will call those are like classical degrees of freedom. And as those, the shape of the fiducial vector depends on those variables, I will call them quantum degrees of freedom. Okay, and in the limit of infinite number of parameters, we can get we can somehow get every wave function, right? We can construct the whole basis of wave functions. So in fact, we'll get full quantum mechanics if we have like infinite number of those additional variables. But it will not give us too much, I believe. But if we have finite amount of those lambdas, we get a very nice truncation that will give us semi-classical motion, and we can easily somehow decide where to cut our how good resolution of how good accuracy of our analysis will be. So just I have a couple of minutes. So just the technical things. So what we did with Przemek, we assumed that the most convenient way to introduce those additional parameters is just to construct those fiducial vectors as a linear combination of some vectors. We use the Hermite polynomials, and lambdas of course are dynamical, right? So we have the constraints. We would like to have this function to be normalized. If those are orthogonal states, then this is the condition. We would like to have these physical centering conditions for both Q and P. And in this basis they look like this. We have some matrices, and the total Hamiltonian looks like this. This constraint is of the first kind, so we can just set C1 to be 0 and just care about those two constraints. And we get the equations of motion for Q, for P, and for lambda. You can see that the symplectic structure is a little bit different, as there's I in here, and the conjugate variables are lambda and lambda conjugate. Okay, so I thought that for the end I would just present you some results, and maybe now it will be more easily seen that why I'm even here. So the first thing, we use the Hermite polynomials as our basis for the fiducial vector. So of course, let's check this formulation for a harmonic oscillator. And in this case, what we get if we put this kind of Hamiltonian into quantum Hamiltonian into the our machinery, we get those classical degrees of freedom decouple from quantum degrees of freedom, and we get just the exact solution of harmonic oscillator. And so if we start with a state which is like, for example, just one eigenstate, during the evolution the state the state stays in this eigenstate. When we start in some mixed state, we get still the exact quantum motion that will not be possible in the standard approach. So actually we get the oscillation between the states. That's something that was not covered by the standard approach without these dynamical parameters. So we thought, okay, so we trapped some particle in the harmonic potential, and it worked very well. So maybe let's scatter. And so I thought maybe just just invert the potential, and see how the trajectories behave. And this is a standard approach. So, well, this is exactly the classical picture. We start from some states which are at q, I believe, -1. They have some momentum, and if they have enough energy, they go above the barrier, and if they don't, they just, well, scatter, right? They are yeah. And, well, so the thing is that, well, maybe we thought maybe with this extended approach we can catch the tunneling, something which was not possible. Oh, okay, I'm finishing. And in fact, well, if we extend our approach and use this extended, well, we can see that some states can just go, which don't have enough energy, they can still go around the barrier. Okay, and something what was mentioned earlier, well, with this kind of analysis, if we have this half plane, there exists some, there appears some repulsive potential. So the classical free particle, which is like this behavior is singular, gets, well, like, well behaving. There's like bounce, right? And, well, we
but this is this approximation where you don't add this additional parameters.
Yes, yes, this is a standard approach. But if we employ our, well, this extended approach, we'll get almost the same term, except this this is not a constant. This gets, well, dynamical, and, well, so this Friedman-Robertson-Walker universe with some proper choice of lapse function can be seen as a free particle. If we start to, well, analyze this, well, the semi-classical motion of this kind of Hamiltonian, well, we will also obtain the bouncing cosmology, and in terms of Hubble parameter and scale factor, well, we get nice proper bounce. And the last slide, I believe, well, I just wanted to point out what happens underneath. Well, the Q is bounced, well, the P changed sign, and those kind of additional parameters somehow feel that there's something strange going on at the bounce, right? And what is more, well, the standard deviation, well, or just the dispersions of scale factor and Hubble parameter, well, just get, well, they are not symmetric, okay? So not clearly visible, but in fact we get something which we'll call like the non-symmetric big bounce, and well, that's almost what I think that's all. I don't have much time left, so I will just finish at this stage. Thank you very much.
You obtain nice approximations.
Yeah.
Okay. Some comments or
Yes, please.
Just a comment.
Okay.
With Artur Miroszewski, I tried something which uses a different formalism, but it looks very similar.
Mm-hmm.
And
but again, who? Because I.
Artur Miroszewski.
Okay. Mm-hmm.
And we tried many different things to get focus in the classical dynamics. It never worked until we realized that we should use Poisson manifolds instead of just vector. With non-invertible Poisson tensors. So do you see a chance here to extend this? So the way that you always have these lambda and G's as canonical pairs. Can you make it just Poisson instead of something?
Well, so at this stage, well, I see the formulation in, well, very symplectic form, right? But, well, that's an important point, right? To generalize it to, well, Poisson. Well, I will absolutely think about it, and it may be a very good, well, advice to look at it. Mm-hmm.